Hello again, guys. I am Andres. As you know, I am a currently chemistry teacher and examiner. So today we'll talk about atomic structure in the syllabus and the IB syllabus. This is the 1.21. Okay, so let's start it. Okay, guys, the video structure is the following. First, I will talk about the learning objective, then I will give the explanation of the topic, and finally, we will practice in past papers questions. What you need to know here in the atomic model is that atoms contain positively charged, dense nucleus composed of protons and neutrons, which are the nucleons, and negative charge electrons occupy the space outside the nucleus, the structure 1.21. The learning objective in this case is use the nuclear symbol. I will talk about what is this nuclear symbol, what is A, what is Z, and what is this X, to deduce the number of protons, neutrons, and electrons in atoms and ions. So that will be the topic today. Always when you hear about the structure of the atom, he was the first that started to study the atom, what is it made of, what is the role of the atom in the world, and these kind of things. The thing is that in all of these studies, there are different and there are like main conclusions that we are keeping at this moment to explain the model of the atoms. Of course, the model of the atom has been updated with time. So scientists, different models and mathematical models have explained the atom in a different way, but Dalton is the one that we need to know. This is like gathering the first ideas and also the Dalton ideas. I will show you exactly what were the statements of Dalton about the atom. So first, those are the three bullet points that we can summarize the whole idea of these conceptions that we have at that time. And is all matter is composed about 100 elements, which cannot be broken down in simpler substances or by chemical reactions. So if we are breaking an atom, of course, we will need to talk about different particles. Elements chemical properties remaining the same even dividing into the small. So if you have a block of one particular element and you break it, these pieces of this element will have the same chemical properties. And there are 92 naturally occurring elements on Earth. Those are the ones that we can found on Earth in a natural way. So here we have, those are the postulates of Dalton model, the first model of the atom. All matter is composed of tiny indivisible particles called atoms. We are still know this. The thing is that we have even more and smaller particles in the current model, but this was what was the one designed by Dalton. Atoms cannot be created or destroyed, but at that time, atoms of the same element are alike in every way. Atoms of different elements are different. Yes, they won't have the same chemical properties, and atoms can combine together in small numbers to form molecules. Remember that, for example, we have H2O. We have two elements. We have hydrogen and oxygen. We have sulfuric acid. We have hydrogen, sulfur, and oxygen. And the thing is, they are in different proportion, create the molecules and compounds. So this is the first Dalton model. Okay, guys, as you know, we have several models of the atom. Another atom is the model of Joseph Job Thomson. This scientist, physicist, he developed this model of the atom. So first of all, it was in 1897 when he set up this experiment. So in this experiment, what you could see here is that it's just a bottle. This is a bottle. Imagine just a bottle of gas. So of course it have a different shape as you could see. So this bottle is sealed all over. So there's no escaping of air. And also you pumped all the air out. Okay. Now, once you pump all the air out, this is how to set up the experiment. There are two pieces of metal. One is here and another is here. Okay, so this bottle with this particular shape is connected to these two pieces of metal. These pieces of metal are connected to this high voltage power supply. What is providing this high voltage supply is that they are working in order to create this beam. Okay, as you could see, this is a beam generated by the high voltage. Okay, but we don't know yet what is that. The thing is that John Thomson saw this phenomena in the experiment that by applying the high voltage is producing what we call the ray tube, the ray. So the experiment, the whole experiment is the cathode ray tube, but we are talking about this spin. When this beam is generated, first, without putting anything else, you could see that one line, one beam is projected. Okay. If there is nothing here interfering, it will go straight. Okay. But the thing is that he discovered that okay, if this beam was created probably made of atoms, I want to investigate more about the nature of the atom. So in that case, Thomson connected a battery. If you could see here, we have the positive and the negative part of the battery. And he discovered that this beam of light, this beam of particles, we don't know yet what this beam of particles bends up toward the positive charge. If you see, it bends up towards the positive charge. After passing through this positive charge, it bends up toward it. Okay, toward this piece of metal. Okay, but what is that? The meaning, and if this bending up towards toward this positive, means that the beam has a negative charge. And this negative charge is what we currently know as the electrons. Okay, so there were different conclusions that he produced after setting up this experiment. So the first conclusion is that the particles made up the cathode rays, these particles, are 1,000 times smaller than the hydrogen atom. This is one of the conclusions. All the element metals used, because he investigated this experiment with different metals. So instead of having iron here, he used, for example, chromium here and different metals. And with the all metals, he discovered the same behavior. Okay, this beam was bending toward the positive metal. Okay, positive charge beam. So in that case, he produced the model that we know that here. Just a J.J. Thomson atomic model when the spherical cloud of positive charge, but it will have negative small charges. In this case, the ones that we know as electrons. And this is like the main idea of John Thomson, English physicist that discovered, or he set up this experiment to make this conclusion of the atom. So electrons. And now we have this new model of the atom. To remember, we have a big positive sphere with a small, tiny negative charges, which we know as atoms currently. This is J.J. Thomson. Okay, guys. Okay. This experiment and this model was developed in 1911. So, what is this about? So, first of all, let's see the setup material. So, for this model, we have this radiation source, and here we have radium. So, you know that radium is an element, a very heavy. So, it means that alpha particles are radiated. Okay, so nuclear chemistry is just a study how very heavy elements with very heavy nuclide um, decay, and when they decay, they release alpha particles. Alpha particles is like a helium atom and is made of four particles, which say that we have protons and two neutrons. We have the mass is 4, and here we have the number of protons is 2. So this is the alpha particle. Okay, we will talk. If you want to get more of this, there is big chapter explaining all of this phenomena. Very interesting. What is important for us is that there is a radiation source which is made of radium, is producing these alpha particles. These alpha particles are produced. Here we have an alpha particle beam. Okay, so called beam is interacting with foil. It is a very thin gold foil. There was a fluorescent screen to see the interaction between the atoms and the gold foil. That was the idea. So as you can see, some particles deflected, some particles bounce, and some particles just change the direction. Yes, if we focus in one of them, let's see this red one, you see that this particle is just changing the direction. This particle is more bouncing out. So here, some particles are going straight. Most of these are going straight. That you see that the angle is changing a little bit. It means that they are deflecting. They are deflecting. So this fluorescent screen is detecting all the behavior of the particles after the okay. Now, with the observations, Rutherford created three main conclusions. Okay, so the first one, when he established that a few alpha particles were deflected from their path, the first conclusion of this is that the nucleus has a strong positive charge. Okay, most of the alpha particles pass through straight through the gold foil, as you could see here, meaning that the atoms are mostly empty space. This is the second conclusion based on the evidence and in the experiment. That the small number of alpha particles rebound. Alpha particles rebound means that they collide with another positive charge. That's why it's bound. It means contain small. So those are the main conclusions of this phenomenon. Okay. Here we have the model of Ernest. Okay, guys, another scientist born only 2 years later in 1913. This Bohr model is about the conclusions that Rutherford discovered about the nature of the atom having positive and negative charge, and also a nuclei, and telling that the discovering that the atom was only empty space, but mostly empty space, establish a theory that is clarifying many things about the atom, and something that still we are using today to explain many phenomena. Okay, this is the Bohr model of the hydrogen atom. Of course, this model also applies to different atoms, but this is a little bit more basic with respect to the one that we are using currently, which instead of orbits is orbitals. Okay, we will talk about this later in structure 1.2. In structure 1.3, when we talked about periodicity and hybridization and this different structure, this Bohr model. The nuclei of the atom has a proton, and the charge of the proton is positive. Okay, this is something that we established. The proton is in the middle of the atom, and that will have positive. The proton charge is positive. There is an electrostatic attraction between the positive and the electron. Okay, that's why the electron is not giving out or is just being attracted to the positive, even though they have negative charge, and it's supposed that if they have positive charge, they attract each other. The thing is that the electron has enough energy to occupy a specific orbit, which has a quantum of energy. So the atom is moving in this orbit, considering this model, um, attracted by. So we have the electron, we have the proton. The size comparison in this Bohr model, where he established that the size of the electron is very compared with the positive charge of the atom, or with the positive proton and the nuclei. Okay, meaning that the electrons are very tiny compared to the. Here we have a table which says that compared with the relative mass of the proton, which is 1, something that we will develop in models. What we need to know now is that the electrons is very small and negligible compared to the proton in terms of size. There is another explanation here about the protons and the neutrons, is that if you see in the nucleus, protons are very close together, and if they are very close together, means that they will repel each other. Yes, it makes no sense that one proton is next to another proton because they have the same charge. If they have the same charge, they will. The thing is that in order to be together in the nucleus, we have some other particles, and these particles are the neutrons. So the neutrons are the ones that balance out this positive charge with some nucleons, some subparticles inside the nucleus as well, the neutrons. And this is how the protons are balancing the positive So if you see, the neutrons exist because the protons need to be close together in the nucleus. Electrons are orbiting around the nucleus. And another very important thing about the Bohr hydrogen atom, something that I mentioned here, is that depending of the energy of in the orbit number one, and then there would be another electron in another energy level, and but in this case, the electron will have more energy than the energy one. That's why is farther from the nucleus, and there will be another orbital here with another n energy. So we could say this is n1, this is n2, and this is n3. So the energies are quantifying in different orbits, in different levels. Okay, the higher the level, the higher the energy of the electron. Okay, and this is the Bohr model. So we will be there because what I am about to explain next is the atomic number and mass number. So for this atomic and mass number, where we don't need to study more orbitals, about the shape of the orbitals, about the current model of the atom, is something that we will explain more in detail when we talked about transition metals and hybridization. But in this case, this is what we need to know, and those are the theories, the three scientists involved in the atomic model. We will talk about atomic number and mass number now. It doesn't mean that the model of the atom stopped there in Bohr model. Scientists, a mathematician, physicist participate in the current model of the atom. And what is important about the atom is a math construction. So we have some orbitals with different shapes that explain how the atom is moving and creating these clouds of electrons with different shapes and in different parts of the atom in the syllabus of the IB. Something that we'll start in transition metals more in depth. But those are the basic models that we need to know in order to understand what is. And here we have the mass number, the atomic number, and the symbol of the element. The mass number will be the number of protons plus the number of neutrons in the atom. So this is the mass number. For example, I will have carbon, and carbon will have a number located in this part. Here we will put carbon is meaning that the amount of protons and the neutrons will add up to 12. And here we have the atomic number. The atomic number here will be the number of protons. So the number of protons will be 6. For carbon, the mass number is 12. The atomic number is 6. If the mass number is the protons plus the neutrons, and I have the number of protons, I just need to subtract the mass number minus the atomic number to find the number of neutrons. And it makes sense. So if I have 12, the number of protons and neutrons, minus 6, the number of protons, then I will have 6, which is the number of. It's so easy. This is how we identify the number of neutrons in a particular atom. Another example, let's talk about nitrogen. We have 7 as the atomic number, and we have 14 as the mass. We have oxygen, which is 16, and here we have 8. 16 will be the mass number, and 8 will be the atomic number. We have fluorine. This will be 19, the mass number, and 9 will be the atomic number. So if I want to determine the number of neutrons of oxygen, it's just 16 will be 8, and this will be the number of neutrons. Okay, now we will talk about the ions. So before explaining using this example, I want to show you a very easy method to understand what is an ion, considering the positive ions named cations and the negative ions named anion. So let's imagine that you have an atom. So, and this atom, let's put this, we have an atom, right? So in the nucleus, we have a proton. Imagine that this is the atom. And here we have an electron. This is the negative charge, and here we have the positive charge. Here, I will put the overall charge of this atom. Because we have -1 and we have +1, the overall charge is 0. -1 plus +1 is 0. Now, what happens if I remove the electron from the atom? Remember that the proton has a positive 1 charge, and I remove the negative 1. What will be the overall charge of this atom? The only thing that you have is positive 1, meaning that positive 1 will be the charge of this atom, right? So this is a cation, and the charge of this cation is positive 1. If you have another atom, you have two positive charges, and then you have two negative charges. What will be the overall charge? If you have two positive and two negatives, the overall charge will be 0, because positive 2 plus negative 2 is 0 as well, right? But what happens if I have this atom, two positive protons in the nucleus, and then I have a negative electron? So that will be two positive plus one negative. What will be the charge here? That will be positive 1, you see? So in this case, this negative electron and this positive, they cancel out, but at the end we have this positive charge. This is another thing, right? So let's imagine that we have here another atom and two electrons. What is the overall charge again? Positive 2 and negative 2. The overall charge will be 0. But now I will remove a proton. Let's say I cannot remove protons, but this is for you to understand what that means. Better, instead of removing the protons, I will put another electron and three electrons. Now, if we have electrons here, two positive charges, you see this negative charge, this positive charge, they go. This negative charge and this positive charge, they go. What is the leftover here is negative. That's why the charge of this atom will be negative 1. In conclusion, if you have more protons than electrons, that will be a positive charge atom, which is a cation, and if this has more electrons than protons, a negative charge, an ion. Okay? Now, here we can use this example of aluminum. If you see, and remember what I explained before, we have aluminum positive, we have 13, but we have a positive 3 charge. Remember that what I said before is that we have a positive charge is because we have more protons than neutrons. If you compare 13 and electrons 13, this is the positive aluminum. But in order to get positive 3 means that I will need protons 13 because I am not removing 13. And what do I need to get a positive 3 here? How many electrons do I need to remove? 10 electrons to get a positive 3, you see? Number of protons minus the positive charge that we have, and that's why we have 10 electrons, okay? So the atom has lost 3 electrons. That's why we have a positive 13 protons and 10 electrons. Now, if you need to determine the number of neutrons, remember the formula that neutrons is equal atomic mass, which is 27, minus the number of protons, 13. It means 14. 14 neutrons. So for this atom, for this ion, because it has a positive charge, we have 10 electrons, we have 13 protons, and then we have 14 neutrons. Okay. Okay, guys. Now we will solve exercises. This is a past paper, but please, if you have enjoyed, if you have learned, please don't forget to like the video and also subscribe so you have more explanation like this. Now, in this exercise, this is state the number of each type of subatomic particles in the potassium ion. 41 mass number and 19 atomic number, but it has a positive 1. Remember that this is an exercise for a past paper, and this is something that they probably will ask. Okay. Now, number of protons. How do we know the number of protons? So I don't need to think too much about this because the number of protons will not change. So the number of protons that you have here is the number of protons that you need to put here, 19. But now the number of electrons. What will be the number of electrons? So remember that if you have 19 protons, then I need to subtract the number of positive charges, which is 1, and then we'll have 18 electrons. So remember that in order for the atom to get a positive charge, it will have more protons than electrons, and makes sense. So electrons will be 18. And how do you determine the number of neutrons? Remember that the number of neutrons equals the mass number minus the atomic number equal the number of electrons. I want to use the conventions that we use here, A minus Z. So number of neutrons will be 41 minus 19. What will be 41 minus 19? Here we have 22. Neutrons 22. So looking at the mark scheme, this is what we got, 19, 18, and 22, using exactly the method that I explained, very straightforward method, and it's very easy exercise. Probably we'll have the exercise at the beginning of the test in paper 2. What is the correct number of subatomic particles for selenium 79? Remember that subatomic particles is about protons, electrons, and neutrons, okay? Now, the first part is the proton. That number will never change, okay? So that will be 34 protons. Then we need electrons. Remember that if the atom has a negative charge, it will have more electrons than protons. If the number of protons and electrons is the same, the charge is 0. Okay, so it will be 34 plus 2, because it's a negative charge. Remember that when we have a positive, we subtract. That will be 36 electrons. And neutrons will be the atomic. It will be the mass number minus the atomic mass, as we show you here. So the mass number is 79 minus 34, and here we have 45 neutrons. Protons 34, electrons 36, and neutrons 45. Let's see here what matches here. It will be here 34, 36, 79 is not here, 34, 36, 45. So meaning that that will be the answer B, right? Now let's solve another exercise. Now here we have another one. Remember that this is the experiment that we use in the atomic model of the atom. Joseph Thomson was the one that created the experiment of the cathode, and he developed that beam, and the beam was charged with a negative beam or a negative particle, right? But in this case, this is reflected and is going towards the negative part. Okay. It says a beam containing two different kind of particles is passed through opposite charge plates with the result of the diagram. This is the diagram. So if you see, we have the positive charge here, and then we have the negative charge here. So this is deflected toward the negative part. If this is deflected toward the negative part, we could say that the nature of the particle 2 would be positive, because it's been attracted to the negative, and particle 1 will have a neutral nature. Particle 1 has a larger mass than particle 2, so they are trying to trick us. Particle 2 has a larger mass of particle 1. We cannot discuss about mass because it's not clear which one will have more mass or less mass, and we are talking a beam, right? Particle 1 is positive charge. That is not true, because positive, this particle 1 goes straight, meaning that is not interfering with the positive negative plate, so there is no charge. And the particle 2 is positive charge, so let's highlight this with green. That will be the correct answer for this exercise. It will be the particle 2 is positive charge. Okay, here we have another past paper exercise. It was which quantities differ between the two species represented by the notation. Okay, we have this tellurium and iodine. Let's calculate very easy. So protons, electrons, and neutrons. So try by your own, stop the video, and then confirm with my solve. Let's keep a little bit more space here. Let's solve tellurium first. So remember, we have the atomic number. The atomic number will be the number of protons, which is 52. The number of electrons, since this is neutral, the number of electrons will be 52, and the number of neutrons will be 128 minus 52. So let's do this. 128 minus 52, that will be 76. Now let's do it for iodine. Here we have number of protons is 53, because this is the number that we have here, the atomic number. Number of electrons, it has a negative charge, meaning that we have more electrons than protons. In this case, it's only one. That will be 54 electrons. And number of neutrons will be 128 minus 53, which is 75. Okay, if you see, protons is different, electrons is different, and neutrons is also different. Let's see the options. The number of protons only. Let's read the question again. Which quantities are different between the two species? No, that's not true because not only the protons is different. The number of protons and the electrons only? No, it's not true because also the neutrons. The number of protons and neutrons only? No, because also the electrons. And the number of protons, neutrons, and electrons. Yes, that's the correct answer. Let's check the mark scheme. Yes, we have the correct answer. Now, guys, those are some exercises that could show up in your test when you are sitting it in your school or when you are sitting in the real exam. So I highly recommend to practice these exercises. Now, here we have more exercises. You can stop, take a screenshot, try by your own. This question 1, question 2, question 3. This is our taken from the IB book. Pearson, here we have another one. I will be safe being a student that is able to solve all of these exercises very easily because those are the exercises that can show up and this is the understanding that you need. Here we have my references. This is the day for today. If you have questions, if you require the mark scheme for this exercise that I just shared, please let me know in the comments. So have a good one and see you in another video.